Great. All right. So welcome, everyone. As said before, my name is Gina, and I'm the outreach coordinator at NOVA, broadcasting to you all the way from Boston. Welcome to Getting Sucked In, Black Holes Research, or Black Holes Outreach. I'm here from NOVA, which is the most watched primetime science series in America. It reaches over 4 million viewers every week. And we've been on the air on PBS stations across the country for over 40 years. And we're really committed to telling the stories of science, from the greatest breakthroughs in technology to unraveling some of the mysteries of the natural world. And today we are going to focus on one of those mysteries of the natural world. And I'm really excited to be joined by another science powerhouse that is on the other side of the country right now. My fabulous partners from the Astronomical Society of the Pacific, who will be hosting this webinar with us tonight. So we have Vivian and Teresa and Brian and Dave on the other side of the country right now. And we're really excited to bring you this webinar that is dedicated to one of the most intriguing objects in our universe, black holes. So the great thing about this topic is that adults and young people alike are really curious about black holes. How do we find them? Where do they come from? What's inside? So today we're going to spend the next 30 or so minutes reviewing a variety of hands-on activities about black holes that are perfect use for an outreach table with your students or potentially inside on a cloudy night. So to kick us off, my hosts at ASP are going to share some hands-on activities that can be done with minimal materials, but also stress how science uses indirect evidence to study things that we can't touch. And then I will round out the webinar with a demo of NOVA's iPad app, Black Holes. So if you have any questions throughout the webinar, feel free to drop them in the Q&A section, and we'll try to answer as many as we can. The chat feature is great for comments and connecting with one another, but make sure you put your questions in the Q&A part, and we will get to them throughout the webinar. So with that, I'm going to pass it off to Vivian and Teresa to get us started.
Well, thanks, Gina. I'm Vivian White.
Hi, I'm Teresa Summer.
And we are coming to you from the Astronomical Society of the Pacific in San Francisco. Cold, freezing cold summer in San Francisco, California.
Yeah.
And before we get started,
we want to know who you are. So if we're going to have a poll put up, and you'll see that in your, should pop up on your screen right about now. And if you can choose who you are, what's the best description for you. We have some teachers checking in, librarians, amateur astronomers. Those are our main groups. We're going to just have that poll for a couple of minutes, and we'll get some feedback to you in a minute.
And while you're doing that, I'm just going to tell you a little bit about the Astronomical Society of the Pacific. We are an astronomy education nonprofit, and our mission is advancing science literacy through astronomy. So we work with educators of all types, informal and formal, and we highlight the best practices of our community. So we've worked with many of you before, and we're excited to see a lot of names we recognize, but it looks like you probably all filled out the poll by now. Let's see who's here. Oh, we have the amateur astronomy community representing. That's all of us at the Night Sky Network. Hi, everybody.
Yep, that's almost 50% of you are amateur astronomers. Coming in strong also are teachers and other higher education staff and faculty, maybe some of the same folks. So we also have librarians and other, that ubiquitous category. We're happy to have all of you here with us today.
Thank you for joining us. I think that you will probably, some of the amateur astronomers are, might recognize some of these activities because these come from the NASA Night Sky Network, a collection of activities and outreach materials that are great for amateur astronomers or other informal science educators. So with that, we're going to talk tonight about indirect evidence, right?
Yes, and I got you a present, Vivian.
Teresa, you shouldn't have. Thank you so much. Ooh, look at that. What could it be?
Oh, you're always so curious.
There are lots of ways I could try and figure out what's in here without opening it. There's some things I can definitely rule out. It is not the pony that I wanted. Thank you, though. Anyway, and I know that it's probably not a watch or a pen. I can shake it, and I can use indirect evidence to get some idea of what might be in here. But indirect evidence is something we use in science a lot.
Right. So just like we can't open that present, well, we can open the present and find out what it is tomorrow, right? But today, when we look at the sky, we can't bring a star down to the lab and dissect it. We need to explore that with our eyes and our tools, detectors that can see different types of light. And we explore all of the phenomenon in the sky that way, except for black holes, because black holes don't allow light to escape. So they don't allow anything to escape, and we can't detect them in that method. So what we have to do is use the light to find other things. And what we look for is the indirect evidence of stars behaving strangely.
Yeah, so until recently, light was our only option of how we got to explore the universe. And we're going to show you now how stars interact around a black hole. And for this activity, we're going to make a model of space and stars, and we're going to use these magnetic marbles that I have here. So let's see. This board over here, are we switching over? Thanks. This board here represents space. So I have a cardboard here, and we're going to roll these marbles across, these stars, across here to see if we can tell. Whoa, first one. I caught something. Something happened here, and I'm not sure exactly what's going on. Whoa, that was a good one too. Okay, so, oh, wow. Oh, man. All right. So stars are affected by black holes, even though we can't see them. A lot of times they will deflect. I don't know if you saw that purple one, deflecting a little bit. Oh, and sometimes they get caught around black holes. But that one, for example, you can see how it moves around a black hole. Now, astronomers are looking for black holes all the time, and this is one of the ways we detect them. Magicians never show how their tricks work, but astronomy educators do. This is just a piece of black. You can use cardboard, and this is another piece of cardboard, and we have got magnets in here. Now, we should note that this is a model, and with models, you're always going to be able to show some things, and it won't show everything. So magnetism is similar to gravity in that it pulls, but also magnets have polar sides, so it pulls and pushes. Gravity only pulls, and of course, these are not really hot stars, they're just marbles. So
don't lose them.
Yeah.
Don't lose your marbles.
Don't lose your marbles.
Right. So what we're going to look at now is a short clip from a video. In the PBS Learning Media Collection, there's a clip there's lots of clips from black hole hunters, and this is about Dr. Andrea Getz. She took pictures of the center of our galaxy, and that shows exactly what we just saw in the model, stars being turned or affected by the mass in the center of our galaxy. So here we go.
These are a factor of 20 sharper than if you had done nothing. And for the first time, we can see the center of the galaxy, and in particular, these stars. They're the ones that are going to tell us what's at the center of the galaxy. So we started off in 1995, and every year since then, we've taken an image. Just take a picture, and you watch how things move on the plane of the sky. Up to 10 million miles per hour. They're really hauling. Four million times the mass of the sun. This is the proof that there's a supermassive black hole at the center of our galaxy, and that supermassive black holes really do exist. I think we have people convinced.
Well, I love this. The whole series is fabulous, but those little clips are great for sharing with other people when you want to illustrate some concepts. So I think there are 7 or 8 of them, Gina, is that right? Yeah, they're really nice and nice accompaniments to the whole video, but also just great to show on their own. So it was just the tail end of one of them. Dr. Getz is an amazing astronomer, and she has made a lot of important discoveries. If there are any questions before we go on to the next activity, I'm going to show you a couple more with some different materials. Feel free to put them in the question and answer section. I think there's a note about where there'll be notes or slides afterwards. Yes, so we don't have too many slides. I will put all of the URLs up at the end, so you don't have to worry about copying anything down. And this video will be available for download on YouTube, as well as we'll have it on the link at the end of the webinar. So unless there are other questions, I think I'll get started on the next one. Okay, so the next thing that we have to show are called gravity buckets. And these are fabulous. It's super easy to make them. They're just a planter, a plastic planter from a landscape store. We've got bi-directional stretchy fabric. That's really important. It needs to stretch in both directions. And then just a bungee cord. So we use that and some regular marbles. We don't have to use the magnetic marbles on this one. So let me switch over. We start, when I am at an event, I say, hey, how high can you guys jump? So that the audience gets excited, the kids start jumping around, and it brings lots of other people over to you when you are standing there. So people want to know what you're doing. And so these buckets we're going to use for two different demos today, and they're both discussing gravity. And this, we are saying, is a model of fabric of space-time. And we're going to use two different very heavy lead weights. Now you want to paint these lead weights because you don't want to just be hanging around with lead too much. It's not so good for you. So we painted them with a little bit of the heavy covering. So what we're going to do is I'm going to say this is a model of space-time. We're using the gravity. We're going to use these buckets here. And this, I'm going to put an Earth here in the center. Let's see what happens. Thanks for getting excited, Teresa.
Big hole there.
Great. We're working in 2D here. We know space actually happens in 3 dimensions, but that's one of our limitations of this model. So the moon, however, is a lot less massive. So compared to the Earth, the moon is much less massive. What do you notice about that?
It hardly makes a dent.
Right? Exactly. So when we're talking about jumping, did you know that you can jump 6 times higher on the moon than you can on Earth?
Wow.
I know. So if you just jumped about a foot, you could jump 6 feet. That's this high when you're on the moon. Let's check out and see how hard it is to escape the gravity of Earth versus the moon. Whoa. Yeah, exactly. So it's you have to push much harder to get out of this gravity well. So anything with mass creates a gravity well in space. This is it inspires a lot of questions around gravity, and that's fabulous. And it also it'll bring up a lot of different questions. So you might want to have, there's a frequently asked questions piece to the activity, so you can have that, just a one-sheeter with you at the table if you get questions that you're not quite sure of the answers. And then there's also a full write-up, so there are many different ways you can use these. Alan says on the chat there that they're a big hit at their outreach events. Thanks, Alan. That's fabulous. Yeah, we have a lot of fun with them when we go places. They're very easy to make. So there's a second activity. When you put these out, people will just want to start exploring with the marbles, and that's really fun. The second activity relates more directly to black holes. And this one, for this, we use a bucket, but we tie the bottom in the center with a string. So there's a little marble in there that we've tied up, and we've pulled it all the way down the center so it goes all the way down deep. Okay, so I'm going to switch back our cameras quickly. Yeah, so this one we're talking about, let's move these. The difference between just a star, for example, like our sun, and a black hole. Well, a black hole warps space much, much more. There's a common misconception that the sun will turn into a black hole, and that's on the frequently asked questions. It will not turn into a black hole. It's not big enough, but only very large stars become black holes. But we're going to look at the difference between what happens when something's near a star, like our sun, and what happens when it's near a black hole. And you can see that this marble is following those same orbits that you saw in the video. You can get stuff moving around. It's really fun. You don't want to get too close to a black hole. We call this activity informally, do black holes suck? What they don't do is suck. It's not like they're big vacuum cleaners that go around the universe. These are actually, it's just that you don't want to get too close to their gravitational well. So these are fun, interactive ways to explain gravity. The Night Sky Network has a lot of interactive activities that you can use like these on many different topics, but there's not just hands-on ways to explore. I want to turn it over to Gina and allow her to show us this really cool new app that comes out, that's come out from the Black Holes Nova special.
Awesome. Thank you. Great. So just a reminder, if you have any questions about anything that Vivian or Teresa have said, please feel free to drop them in the Q&A and we will monitor them the whole time. And I see that Dave's dropped some links to some of the Night Sky Network activities we were talking about, and some links to the NOVA playlist for all of our short form videos in the chat section. So keep an eye out on that. So yeah, I've heard, so some of the videos you saw, and really the inspiration from this webinar is in January, NOVA released a 2-hour special called Black Hole Apocalypse that was hosted by astrophysicist John Levin, who, which is important to note, is our first female host that we have ever had on a NOVA. And it only took us 45 seasons, but you know what? We made it. It's okay. So it's a feature that takes a deep dive into the physics behind star formation, black hole formation, and the scientists that have dedicated their lives to answering questions about one of these most mysterious objects in our universe. So here at NOVA, we like to make an education component for each of our films. So we know it's not realistic at an outreach table or at a museum or in your classroom to show a 2-hour film. That's just not always possible. And so we figured, why would we just tell people about the science and we can show them and they can experience it themselves, or as close as you can to touching a black hole. So we decided to make an app, and that's how Nova Black Holes was born. So this app was released in 2016, and currently it's only available on the iPad. But we are hopefully going to change that in the future. So I'm going to give you a little bit of background about the app and what you'll do, and then I'm going to share my screen and you'll actually see it in action. So this game is targeted for 6th grade and up, but I've been taking this app across the country for the past couple months, and I've seen people of all ages play this game, as young as 5 and as old as 50, and across the board, 5 stars. Everyone has loved it. So you don't need a really strong grasp of astrophysics or gravity or anything like that. It's a learn as you go. It's a really inquiry-based game. Unlike our examples before, where we heard a lot of an educator or someone doing outreach, it would be really beneficial if someone was guiding you through this process. What are you seeing? What's happening here? What's happening there? This app is much more self-directed. So say you had a substitute, or it's a cloudy day, or it's a daytime session and you're looking for an independent activity. This could be a great fit, as you don't need an educator to lead this activity. Students can guide themselves through the app on their own. It comes with instructions, goals, explainers, and then students can kind of lead themselves through the inquiry process. So without further ado, I will share my screen. And oh, you're going to see my camera roll for a minute. Hold on. Zoom. Start broadcast. All right. Can everyone see my screen? Okay.
Yeah, we see you.
Perfect. Thank you. All right. So this is what the first interface of the app looks like. So there's an option to watch the entire Black Hole Apocalypse film straight through the app, which is what the watch button says. But we're really here for the meat. So we want to hit play and we want to get started. So as you'll see, we have about 53 levels in total, and they're broken up into 9 missions. However, you have to beat 1 mission at a time in order to get to the next one. So you'll see there's a lot up here that have been completed, but there are some down here that are locked. So all the levels really build off of each other, introducing new components, and they get more difficult as you go along. So the other great thing is that this game brings a lot of the concepts we talked about earlier. So objects with more mass, having more gravity, bending space-time, all in one digital format. So the goal of this game is that you are a star. So let me pull up the easy level so you can get a sense of what it looks like. So this is our space-time grid. And as it says in the top, to win this level, you need to blast your way through multiple red dwarf targets. So I am this yellow sun right here. And my goal is to hurl myself through the galaxy and crush these 3 red dwarfs in front of me. So what I can do is, if I want to learn more about these stars, I can tap them with my finger. And it'll bring me up close and personal to the star. It'll tell me a little bit about the star. It'll tell me about its mass and its radius in relation to the sun or the earth. And I can go back. And what I do is, it's kind of like if anyone's played Angry Birds, it's a very similar concept where I tap on my star. I choose my trajectory and my velocity by how far I want to pull back. And let's say I want to do that. And let's see how it goes. Woo! Great. So you might have noticed that as my yellow star goes through the galaxy, stars obliterated, really for that positive reinforcement. So as my star goes through the galaxy, you can see the bending of space-time. So you can see it a little bit on the edge of my yellow star right now, but watch as I slingshot it again. Oh, let's see if I can get this one. Yes, great. So that way, whoever's playing your game, young people, visitors, can get a sense of how space-time is bending as objects are moving through. So my goal is to ultimately collide with all of these stars so I can eventually gain enough mass to become a supermassive black hole. So you can see that levels get a little bit harder. So now we're dealing with binaries. So I have to calculate my my angle and my velocity based off of the position of the stars on the grid. And one thing that's really important to note is that this is just a model. So it's definitely not a perfect representation of what's happening in space at any given moment, because stars rarely collide and they aren't hexagons. But it's a great way to see and experience gravity's pull on other objects in the universe. So like we mentioned before, this is a great resource if you're running an astronomy programming during the day, or if it happens to be some cloudy. So I'm going to jump to some of the harder levels so you can see how play gets more difficult by adding objects with more mass, multiple targets, or even some invisible objects. So let's go to, okay. So you'll see this level's a bit different. The space-time grid is much bigger. You'll see that this star right here has much more mass and the space-time is bent a lot more. This blue supergiant. And then we have another one over here. Another blue supergiant. All right. So this one gets a little harder because what I need to do is I need to navigate around the gravity of this object. See how it's slingshotted around the star in order to hit my target. So this is where students are really participating in inquiry. They're making an observation of saying, okay, this is how deep that gravity well is. If I try and go around it this way, I think this will happen. They'll see that observation and then say, okay, that didn't work. What if I try this? What if I try that? And it's really in a more fun gamification format. So students can win badges for every so many levels they complete. And if they complete all 53 levels, then they get their final badge. So as we get a little harder, you'll see that black holes actually appear on the space-time grid. So you have to navigate this black hole in the middle, and you can see how deep the space-time grid just bends down. It has the mass, it has the radius, it even shows the accretion disk, which is really cool. And you can see that if you try and go around it, it's much more difficult to get sucked in. and you can kind of see how things move around the grid. This game is, if you've just watched me play it, it's a little challenging right off the bat. And sometimes young people can get frustrated if they don't know the answers right away. Well, one other great thing that NOVA does for everyone is that we have this resource called PBS Learning Media. We have over 900 resources on PBS Learning Media from a lot of our different shows, and Black Hole Apocalypse has its own special collection. And the app is featured on this collection. So right now I'm on the PBS Learning Media page for Black Hole Apocalypse, particularly for our Black Holes app Educator guide. So on this guide, say you're having some levels that you're having a challenge with, you can click on NOVA Black Holes level guide, and right here it tells you the answers to every single level if you're stuck, with a little bit of a tip for all 53 levels all the way at the bottom. Also comes with the app is a celestial objects guide. So it tells you a little bit more about some of the objects that you're going to encounter throughout the app. So we have exoplanets, neutron stars, dwarf stars, black holes, quasars, basically anything you can encounter with a little bit more information about that object. Also on PBS Learning Media or on the NOVA Black Holes Educator Guide, you can look down. There's a little bit of a lesson summary. So our objectives for the app, so what we're trying to do, some explainers on how to play. And then on the bottom, you'll see we have some support materials. So if you click on the support materials, we have some discussion questions. So say you wanted all of your young people or your visitors to just work on mission 1. So it's about 3 to 5 levels per each mission. So then you can have them do this. Everyone take a pause. All right, let's talk about some of these questions. What are you seeing? And we have those questions for each mission. We also have some teaching tips that are some just like best practices for implementing the app in your classroom or in your museum or anything like that. And then if you are in a classroom setting, we do have how this app aligns to educational standards, particularly for NGSS. So also on PBS Learning Media, you saw that brief clip of Andrea Getz. That is from our Black Hole Apocalypse collection. So as I mentioned earlier, not everyone has the luxury of showing a 2-hour video in their classroom. So we have cut up that video into about 5-minute standalone chunks that you can just pull and play in your classroom at any point in time. So say you're not really interested about star formation, but you really want to talk about gravitational waves. This is a 5-minute clip from our the gravitational waves portion of the show. So you can pull it up in your classroom. You can show it in class. This comes with it should come with, so this has teaching tips as well, like when you can use it, how it aligns to NGSS and other state standards. And then most objects, it doesn't look like this does, come with a background essay. So say you're not an astrophysicist, I'm not either. But I need a little bit more background information about this topic before I teach it in my classroom. So most assets will also have a background essay to give you a little bit more about that a little more information about that subject before you teach it in front of your students. And with that,
Gina, I noticed that there's a question for you. Greg mentioned that I have the app, but most of the levels appear to be locked. What are your thoughts about that?
Yes, they will be locked until you beat them. So you have to beat them in order. So you have to beat level 1 to play level 2, et cetera, et cetera. So unless you use the guide to get all the way through, there's no way to immediately jump to level 55 or anything like that. You have to play through from 1 to 53. And if you just sat down and did it, it takes about 2 hours. Great.
Wow, that's really cool.
2 hours, that's amazing. That's
Yeah,
right. Content to go through.
It's a lot.
Yeah.
It's really fun. Well done.
It is.
It's a really fun app. It gives kids like a fun way to interact with the science a little bit. And it's it's just really great to have them be able to like guide themselves through it, which is really helpful.
Good. Great.
Cool. Are there any other questions?
Let's go to that Q&A area and see if there's any questions.
Yeah,
If
feel free to
you
add them there.
feel free to add them.
Just say hi. While you're thinking of them, I just wanted to tell you that many of you are joining us are from the NASA Night Sky Network, a collection of over 420 astronomy clubs across the US. I just want to make everyone else who's not aware, let them know that you're welcome to reach out to amateur astronomers in your community. There is an average of 20 plus events per day on the calendar, so you're likely to find amateur astronomy clubs and events in your area. We'll have those links up in just a second. It's also a great repository of informal education activities. So the black hole buckets and the how do we find black holes are both from those collections. So we have those there. They even have star maps of where to find the black holes if you're interested for each of the seasons.
And there's more than black holes there. There's also solar system objects and lessons about asteroids and planets and things outside of our solar system, like extrasolar planets and galaxies and different topics that you could just put in the search for other outreach activities that you could use in a classroom or outside of a classroom.
Mm-hmm. There's a question about the Educator guide.
Yes. Okay. Where are the answers? You do not need to log in to see them. So when you go on to the app Educator guide, if you towards the bottom underneath the download the iPad app here, there's like a sentence or two. And then you'll see two links. One says Nova Black Holes Celestial Object Guide, and the other one says Nova Black Holes Level Guide. The level guide is where you will find, is where your cheat sheet will be.
Great.
Thank you. That's a good question.
Yeah, Dan is asking, is anyone aware of any educational outreach or educational tools available around the new Event Horizons telescope project? If not, it would be a cool thing to explore, which I completely agree. I don't know of any available yet, but I'll keep my eyes out. Yeah, I agree, but can't help you yet.
If anybody has any that they know of, you can share them in the chat.
Yeah.
And Brian Cruz said he might, oh, I misunderstood. Oh, is there any information about Hawking radiation in the educational resources? Gina.
I'm sorry, any information about what?
Hawking radiation.
I do not believe so, no. We have a lot about Cygnus X1, stellar life cycles, gravitational waves, visiting a black hole, gravity and space-time and modeling galaxies. Unfortunately, nothing about Hawking radiation. It might be in the show. I haven't watched the show in about a month or so, but it is not in the educational resources.
It does discuss it some in the show, I remembered.
Yeah.
Yeah, so it is in there. Elizabeth's asking, you never really explained what a black hole does if it doesn't suck. So it's a good question.
That is a good question, and you'll get it a lot from visitors if you have people at your gravity bucket. Basically, because it makes that well, you fall into the well. It doesn't pull you in. You fall into the well. So that's a really good question. The gravitational well just pulls you in if you pass that event horizon.
It's only if you get too close.
Right.
You can get fairly close and escape that, like you can see in the game, in the app. But it doesn't suck you in. It doesn't just go around gobbling things up. Yeah.
There's also a really great, one of the resources we have on PBS Learning Media is Visit a Black Hole, where our host, Jonna, is in a spaceship that can withstand being in the gravitational pull of a black hole. And she actually takes a spacewalk in her spacesuit. And she talks about how time, if you're watching on Earth, based on how she's experiencing time, how it changes because of gravity, what would happen when you go past the event horizon. And it's a really interesting clip that kind of gives people a little more context of what could happen or what we think would happen.
show also goes into a lot of the LIGO detections, and that's really exciting around gravitational waves, and answers a lot of those questions that I know people have when they come to you. Yeah.
One thing that's really great, I think, about the show is that it really talks about the discovery process of science and how science isn't just a collection of facts, but it's a process of doing things, and how we do it matters. So it's a really interesting overview of the topic. Lori Merrick just asked, what is the name of the video that Gina just mentioned?
Yes, so if you're on PBS Learning Media, it's literally called Visit a Black Hole. And that's where you will find it. I should also mention that, so our film that we've been talking about, Black Hole Apocalypse, there are the 8 5-minute clips on PBS Learning Media, but you can also watch the 2 full-hour feature for free on PBS. So if you go to NOVA's website and you just search Black Hole Apocalypse, the full 2-hour film is available to stream on our website. So that should be up for a little while now. Feel free to watch it at any point in time. We also have a bunch of short form features. We have a couple YouTube videos called Black Hole Hunters that highlight some of the women that are featured in our film and their research and how they got into this research, which is really fascinating. There's a lot of other short form videos, some written articles that we've done. So feel free to comb through our website. We have a lot of different resources for you.
Great. William Mitchell was asking how we relate the gravity well in the space demo to the downward drop of an object on the surface of the Earth. I usually relate it to the upward push, and that's where it comes in with black holes as well. So you can jump, and if you jump with enough force, or if you are a rocket, you could actually escape Earth's gravity well. Well, you have to be going pretty fast in order to do that. But if you were trying to get out of a black hole, you couldn't even travel. It wouldn't matter how fast you traveled, even the fastest you could possibly go, the speed limit in the universe, which is the speed of light. Even if you went that fast, you couldn't escape, which is why it traps everything. So I talk about the gravity well being how hard it is to get off of the surface of the Earth often, or the surface of anything, and how impossible it is to do from a black hole. Yeah.
And Ray asked, how do you explain or demonstrate the time component of the space-time continuum? And it's interesting that you say that, because Vivian was like, don't call it the space-time continuum, or we'll make people have a whole different concept that we have to explain. So here we are explaining it, right? Basically, we don't have a demo that explains space-time continuum because it is a tricky concept. But for me, the key takeaway is that as you approach the speed of light, your time moves faster, and your space also gets affected.
Slower.
Your time moves slower,
Yeah,
yes, and your space gets longer. So it just shows that there's a relationship between the space and time continuum, that they're connected, that they're the same phenomena. Through the constant of the speed of light. I don't have a demo about that because it's kind of outside of the realm of our Earth, right? You can also talk a little bit about how satellites have to adjust their time microseconds for their clocks to relate to the clocks on Earth. But it's really, it's a good question and a tricky concept to explain, but I'm always for adding a little bit of knowledge and leaving them wanting more, as opposed to closing down those questions. So keep asking them and keep trying. And if you find a good one, let us know.
I think it was Carl Sagan. I really liked his explanation of it. He talked about how, let's see if we can do this on here. This was not planned. That we're living in this 3-dimensional space, but let's pretend we took it down to 2-dimensional space. They say time is like the 4th dimension. So, right, we can't see it. We can only see the present. But time is our 4th dimension. If we imagine instead living in a 2-dimensional space, and if you're on this, you can't see up or down. You can only see in 2 dimensions. They're all around you. But imagine I took a pencil and I pushed it right through here. First, you would see a little round, you could see all around it, there would be a little round tip of the lead of the pencil, say, and then it would change over time, over your time here. And you would see it change, but you wouldn't be able to see what's coming before or after. I love how he explained time in that way. That's one of my favorite explanations. Let's see, somebody also just found a good resource on the Event Horizon Telescope. It's in the, if you just go to eventhorizontelescope.org/science, it looks like they're working on the first image of an accretion disk around a black hole. Wow.
That's exciting.
Thanks, Dan.
Thanks. That's in the chat. So if you want to check out that resource, you can go ahead.
Absolutely.
And Brian and Dave, our colleagues, have also shared some information in the chat, some good links. Speaking of links,
Yeah.
maybe we should share some with you about some of the resources we talked about today.
Oh, yeah, absolutely. Let's see. Yeah, we usually refer to space as well. I think that might be an easier way to do it. I just want to put these links up here so you have access to all of them. Thanks, Dave. Great. So this full webinar and lots of the things that we talked about during the webinar will be available on this top link here. Let's see.
Oh, one more question came in. How does one explain the ocean staying on the surface of the Earth without being spun off in terms of gravity wells? Viv?
Yeah, I like that one. I relate it to being on a train, like you're even though you are moving very fast, your water is not flying off because it's right there on the train with you. I was working with some nuns and they said, well, we were all the way across the globe in India, and they said, why did you have to fly here? Why couldn't you just jump up really high and wait until the Earth spun and then land? I said, well, it doesn't really work that way. We're on this spaceship Earth. So the oceans are staying on, they are held on by gravity, and they're moving with us. Yeah. Good question. Cool. Oh. Let's see, anybody else before we go? Can you see the slides up with all of the links? I don't think we have that up right now. Sorry, give us 1 second. There we go. That's the one.
There we go.
All right. So it'll all be on bit.ly/BHNSN. You can find all of these links on there as well. So one in particular, they're right there. But this full webinar, we'll have it posted on there within a couple of days. Yeah. So thanks everybody for joining us. I really appreciate it.
Yes, thank you so much. And so I really want to thank Astronomical Society of the Pacific for hosting this with me, and for everyone else to come out tonight and take some time to learn about black holes. It was great. Thank you for your questions and your time. If you're looking for more resources, please visit those links, and you can download this at any point in time. And if you have any questions about NOVA and what we do, feel free to reach out to me. I'm sure the same with ASP. And thanks for having us, and have a great week, everyone.
Thanks for joining us and spending your time with us too.
Thanks, Gina.
Thank you.
Good night, everybody.
Night. Bye.
Bye.